Welcome back. The next step is to analyze a Carnot cycle. But before we do that, we must be very clear about what we mean by a reversible process. We have defined a reversible process a while ago, and we have also been conscious of the fact that it is a process that we can think about, we will not be able to implement it in practice. So let us see, at least in principle, what does it take to implement a reversible process, so that we can analyze it and complete our discussion. So let us look at what it takes to execute a reversible process. Remember that a reversible process is such that when you implement it in the other direction, the processes are retraced, all interactions take place exactly by the same amount in exactly the opposite direction. No trace ever is left with the system or with the interacting systems that a process has taken place. If you execute a reversible process in the forward direction and then in the backward direction, absolutely no trace. Nobody will be able to even imagine that a process was executed and then executed in the reverse direction. Nobody will be able to determine that that had ever happened. So that is the requirement of a reversible process. So the first requirement is that not only our system and all interacting systems must execute reversible processes. If some interacting system executes an irreversible process, a trace is left. Well then the whole process is not reversible, because history has not been erased. So all systems involved must be executing reversible processes, and that means that a reversible process can only be executed, if at all, in an isolated system, because such a system does not interact with other systems. So our system in which we are interested and other systems with which it interacts must form a larger isolated system, and then we can talk about whether the processes in that are reversible or not. Because it is an isolated system, there are no interactions with the outside world, and hence we do not have to worry about what happens outside it. Within an isolated system, we can then discuss whether the processes are reversible or not. Not just our system, involve all the systems directly or indirectly interacting with our system. The second one is we must be able to retrace the process exactly. That means all states involved, initial, final, intermediate, must be states in equilibrium. This implies that all processes must be quasi-static. All intermediate states very properly defined. The third one, we know that heat can be transferred between two systems only in the direction in which the temperature is reduced. So if you have two systems A and B, if TA is higher than TB in a thermodynamic sense, heat will be transferred from A to B. This is definitely an irreversible process, because the states remain the same, temperatures remain the same, but you cannot transfer the heat in the other direction. This is one of the basic irreversible processes. So heat transfer must take place at 0 delta T. That means if we have a system and if we have another system, let us say this is system X and this is system Y, and if there is some heat transfer taking place, this Tx and Ty must equal each other. Now this leads us to a trap. The science and technology of another field called heat transfer tells us that heat can be transferred if there is a small temperature difference, but smaller the temperature difference, more difficult it is to transfer heat. It will be transferred more slowly, a large amount of surface area is required for that transfer and so on, but life becomes more and more difficult for heat transfer moment you make the temperature differences smaller and smaller. But we are looking at the thermodynamic ideal, reversibility. So we must say that if you want a reversible process, the temperature difference between two systems interacting through the process of heat transfer must be 0. Any finite difference temperature, however small, will not be acceptable. The fourth one, there should be no one-way work transfer. This means if we have a fluid, something like stirrer work is out, friction is out, and related to this, one more requirement, there should be a balance of forces. For example, if our system is expanding, there will be a pressure difference across the piston separating the system and the neighboring system on which it is doing work. This pressure difference has to be 0, because if there is a finite pressure difference, you can't reverse the process. If the outside pressure, the neighboring system pressure is lower, in no way will that be able to reverse and do work on the system. I gave an example of pressure, but you can consider the charging and discharging of an electric cell. The cell has its standard potential. The charging circuit should have a potential equal to the cell. You can't have a higher potential, because if it is a higher potential, during the reverse process you will need a circuit with a higher potential and the current will just not flow through that higher potential. And finally, related in somewhat to the no one-way heat transfer, no dissipative processes. For example, passing of current through an electrical resistor. We know it is a sort of one-way work mode, a dissipative process, so that is out. These are the points which I have listed, which come to mind when you try to implement a reversible process in practice. But the definition of reversibility is not this. This is just a checklist to see that we are not doing anything which is likely to be irreversible. A reversible process remains as defined in our original definition. This is just a checklist. Now we will be using this checklist to set up, at least in theory, in principle, the reversible processes which are required to implement a Carnot cycle, and then analyze that Carnot cycle. Thank you.